Hi, it's Tim. If you drop a mass tied to a heavy wheel, it falls slower than free fall. It feels intuitive, but how exactly does the wheel fight back? Let's look at the exact problem we're solving today. A wheel of radius r, mass m, and moment of inertia I is mounted on a frictionless horizontal axle. A light cord wrapped around the wheel supports an object of mass m. When the wheel is released, the object accelerates downward, the cord unwraps, and the wheel rotates with an angular acceleration. Find expressions for the angular acceleration of the wheel, the translational acceleration of the object, and the tension in the cord. It sounds complex, but it's really just a conversation between two different types of motion, straight line and rotational. Let's isolate the falling mass first. Gravity pulls it down with a force of mg, while the cord pulls it back up with a tension T. Because it accelerates downward, Newton tells us that the net force equals mass times acceleration, which is mg minus t equals ma. But what about a wheel? The tension T pulls on the rim at a distance r, creating a torque that forces it to rotate. Torque is just the rotational cousin of force, so we write torque equals Tr equals I alpha. Here is the bridge connecting both worlds. Because the cord doesn't slip, the linear acceleration of the block must perfectly match the tangential acceleration of the wheel's rim. That gives us a beautiful geometric constraint, A equals R alpha, or simply alpha equals A over R. Now, it's just a matter of substitution. If we plug our expression for alpha into the torque equation, we find the tension in terms of linear acceleration, T equals IA over R squared. Let's substitute this back into our very first equation for the falling mass and watch how cleanly the acceleration isolates itself. mg minus IA over R squared equals ma, so A equals mg divided by m plus I over R squared. Once you have the translational acceleration A, the remaining pieces fall into place like dominoes. The angular acceleration alpha becomes alpha equals mg divided by mr plus I over r, and the tension T simplifies to T equals img divided by mr squared plus I. Notice how the denominator isn't just the mass of the block, but a combination of the block's mass and a wheel's rotational inertia. The wheel literally adds virtual weight to the system. Master the interplay between forces and torques, and you master advanced mechanics. Follow for more, and I'll see you in the next one. Bye.